Okay, welcome everyone to the Air Sea Fluxus from Space webinar series. Today we have George Huffman from NASA Goddard Space Flight Center. He's going to talk about global precipitation as represented in IMERG and GPCP. And we're fortunate to have George, who is really in charge of all this and understands all the details. So take it away, George. Thank you.
Thank you. I'm glad to be here. The part of that details thing is if you use my data set, our data sets, and find things, we answer questions. And that's partly because when you find a skeleton in the closet, there's at least a possibility that I put it there. So don't hesitate to ask questions. Also during the seminar, if you want to ask questions. Of course, I've got too many slides, so I'm going to try to trot through the early material and the late material and give plenty of time for questions. So let's get started. Going to give a little introduction about how we do this, including the algorithms. I will talk about GPCP briefly, and then IMERG perhaps more extensively because it's more detailed, show some climatological stuff, and just end with some concluding thoughts. I've now obscured part of one of the outputs of these, which is grand average climatology from IMERG. When the time that we did this, we didn't have the first 2 years, and since then we do. So this is but it doesn't change that much after 20 years of data. Okay, I want to do a little introduction just to get people on the same page. Remote sensors, specifically from satellite, which is what I do, see a cloud. They see the solid hydrometeors at the top of the cloud, including in the tropics. Those legendary hot towers in hurricanes and typhoons are actually populated by snow above the freezing level, which is somewhere around 6 kilometers. I was a little bit shocked at that, but sure enough, it's true. Liquid hydrometeors below the freezing level, and if there's only liquid, it changes the character of how we do the sensing. And then the rain shaft, which you see below the cloud. In order to do the remote sensing, we use various wavelengths, but there are only a few. And so the visible wavelengths could be used for remote sensing of precipitation during daylight hours, but in fact are not operationally. Infrared, if you'll stand by, it's the cloud pictures that you see on TV at night. And then microwave is broken into scattering channels, which are the lower frequencies, and passive emission channels, which are the, I got that backwards. Scattering channels are the higher frequencies, emission are lower. And then there's the active, which is a radar. The problem with active, of course, is it's more expensive and to build and to operate. So different kinds of instrumentation can be used to do precipitation estimation and sensing. The microwave imagers, which are the lower frequencies, are good at instantaneous results. The microwave soundings, there's some information in cold surface conditions, which is a particular problem for imagers. The GOIR has really great sampling, but these are the strengths. Gauges, near zero bias, and models have the allure of, complete coverage in physics. They're best in different regions, and practically all of these have bigger errors when you get in mountains and snowy and icy regions. Now, if you're an ocean person, that sort of reduces to sea ice or not sea ice. Not too many mountains. Okay, and then there's a whole list of excuses, and I'm not going to go through all these in detail, but suffice it to say, if someone really wants to pound on any of these sensors, you get done thinking that it's no good, which is not true. They have use at some point. Specifically for satellites, the infrared has weak physics, but really great sampling. The microwave has poorer sampling and better microphysics. Additionally, over land, we can't use the emission channels because the land is radiometrically warm and highly variable. There are issues with orographic because if you have, well, I don't need to talk about that in an ocean context, but suffice it to say, there are extra problems in mountain regions. And then the utility over snow and sea ice, in particular, for you, is still a work in progress. So here's an example of nearly coincident views from 5 different sensors. Sort of an old picture because it's from trim, but it's still true. So there are 5 sensors. The offset time from 0Z is given underneath the acronym for each of the sensors. And when you look at these, they're clearly related. You know, they're looking at the same system, but each one sees the system in a different way because of time of observation, resolution, and the sensor and algorithm limitations. So in the combination schemes, we try to emphasize the strengths, you know, weaknesses, do intercalibrations. So the diagrams on the right show you for passive microwave and the GOIR what the coverage is. The GOIR has essentially complete global coverage in the band 60 north to south, and it stretches back, in fact, to 1983. That sort of blank in the, let's see if I can get this. Here we go. Laser pointer. There we go. So this blank, which is over the Indian Ocean, in fact, can be covered if you use the very edges of the geosynchronous coverage. So we can go back to 1983. Despite the hodgepodge of sensors, they're pretty nice. They can be pretty nicely intercalibrated. Passive microwave, on the other hand, is sort of sparse. It only goes back to 1987, and in fact, this first red line, which is the DMSP F8 SSMI, had problems, and so we really only the last since about 1990 do we really get good coverage, any coverage, and good coverage since 2000. So what we want is the longest record of global precipitation. And what are the requirements? Well, besides long-term and global, we want to minimize the random error, which is the part that will eventually average out. So at half-hourly, random error is important. At monthly, it's not as important. And then bias, which is the part that doesn't average out. Typically, the random error swamps bias at the half hour, and by the time you get to monthly, the bias is more important. So there are 2 general approaches. One is a climate data record, which emphasizes homogeneity over the short-term answer. And I've highlighted here the passive microwave that we use in GPCP to accomplish this. So these passive microwave at the 18 local overpass time, and of course 06 at the other side, is all we use to do calibration of the infrared in GPCP. The alternative is a high resolution precipitation product, which emphasizes the short-term answer being right over homogeneity in the long term. And so IMERG is an example of this. In this case, now we use all the passive microwave, all the GOIR. But there are others, GSMAP, which is a companion, the JAXA product, which is the counterpart to the NASA product, IMERG, and then CMORPH, which is a NOAA product, which has been around for a long time. I've emphasized goals for each of these, but of course, the less emphasized goal is also important, and we waste a lot of time in each of the products trying to satisfy the less important goal. GPCP. So we use, I've said this, the 6 a.m. p.m. microwave for rolling regional calibration of the GOIR. And then at high latitudes where the GOIR isn't seeing, as the Earth converges toward the pole, the GOIR isn't terribly useful. And so we use TOBS and AIRS. It's really old data, and we're desperately trying to replace it with something more modern. It's just an inverse error variance weighted combination of satellite and the GPCC monthly gauge analysis. Once again, gauge analysis is not terribly relevant over oceans because we don't use the isolated islands. In general, isolated island gauges are not representative of the open ocean, which is what, that's the large area that we have to represent. The current GPCP is at half-degree lat-long grid starting in 1983. We're actually hung up in March of 2024 right now because the input data set, IR data set, is waiting for a new calibration scheme to move forward in time. We also compute a daily product, and what we use there is use the IMERG final scaled just with a simple ratio each month by the GPCP monthly. Also at a half-degree grid starting in 1998 and coming to the delayed present, where the delay, once again, is based on the monthly. That's a considerable simplification from what we used to do, but it's also more accurate. Version 3.3 was just has been released now. And like I said, it's paused. The normal latency is about 4 months. Here's the URLs to get to the data. It's in the GESDIS, Goddard Earth Science Data Information Services Center archive. And this is currently being funded by a NASA Measures program, which really makes this happen. Okay, so in contrast, IMERG, which stands for the Integrated Multi-Satellite Retrievals for GPM, uses mostly the good stuff, microwave, but it's sparse. And so this shows you for a given half hour what it looks like. And here's the various satellites who contribute, or sensor types. There's multiple satellites. You can see there's several, there's at least 3 SSMISs here, there's 2 MHSs, and so on. In order to accomplish the combination, the US GPM science team developed IMERG, and I lead it. It's an intercalibration to the GPM so-called core observatory reference products. So the core observatory has both a wide range of microwave channels as well as a dual frequency radar. And then we use a so-called virtual constellation of microwave and GeoIR sensors. The idea here is it's virtual in the sense that we don't control any of it. We ask people who are observing in the microwave and GeoIR to send data. The GeoIR is actually combined into one nice uniform field by the people at Climate Prediction Center at NOAA. Then we use the individual microwave satellites after they've been intercalibrated, and we morph them, which is to say we do a Lagrangian time interpolation following the systems. And then finally, we use the GPCC, Global Precipitation Climatology Center, monthly gauge analysis. So we don't do the gauges ourselves, we use their analysis, and it's at a 1 degree scale. It's a little bit coarse, but it's what we use. We're currently in version 7B. It's a 0.1 degree lat-long grid from 1998 to the delayed present. There's various latencies. I think I show that next. It's available on the GPM website, GPM NASA Gov, and go down to data and then directory. I assume these slides will be, or at least the recording will be available for viewing, so you can pick these up. You don't have to scribble furiously. Okay, so here's what it looks like. You have the intermittent microwave data at the top and the nice continuous but low quality IR data at the bottom. And so what we do is we take this snapshot and intercalibrate before we did this merger. And then we have the rolling microwave calibration of the IR to give us something that's, you want the histograms to be consistent. And we do the Lagrangian time interpolation of the microwave. And then we use that with the IR in a Kalman filter scheme It's basically an optimal interpolation based on correlations to give us a half-hourly IMERG. And so now we have a complete global field that emphasizes input from the microwave, but uses the IR where the microwave hasn't been around for a while. We have 90% of the time within 3 hours, we have an observation, but once in a while, it's like 6 or 8 hours, at which point simply moving an unchanging pattern across is not very helpful. So it's obviously its quality is going to be low when we use IR. Okay, so now we get down to the latency. We knew this before, and so when we designed IMERG, we actually decided to produce 3 what we call runs: early, late, and final. The idea here is the early is a first approximation for people that need the data pretty fast. Right now it comes out at about 4 hours. And we acknowledge that the truly operational users, less than 3 hours, are not well addressed. But as a best effort system, we don't think that it's helpful for the truly operational users to depend on us, because best effort means, oh, well, it didn't work today. We don't have hot spares and guys with beepers. The late is meant for like next day use, delay of 14 hours. We wait for a full multi-satellite input. And the driver is that we wait for the microwave data to not just from already happened but for data that comes after the observation time, so that we can do a backward propagation as well as forward propagation. After all, if you're about to have an overpass, you'd really like to know what that number is, because that's probably better than what happened 4 hours ago. So we wait. And as a next day product, that's fine. And then the final run is after the best data are assembled. There are reprocessings for the input data, as well as bringing in the gauge analysis, which only comes about 4 months after real time, which is a driver. This is intended for research users. This, if you're going to do real research, this is what you want to use. On the other hand, if you're developing a near real-time product, either the early or late, depending on how long you can wait, is what you need to use, because we have a complete retrospective processing which emulates the early and late as well as the final for the entire data record, which means you can reliably develop statistics based on the performance of the early and late, if that's what you're using. Okay, rocketing right along. Fine scale variations in the climatology for both land and ocean. It's the case that the occurrence of precipitation is driven by the individual input data sets, which is to say the various satellites. The calibration is intended to enforce a consistency in the distribution, but the occurrence is driven by what happens in each satellite at each time. So the event-driven statistics depend on the satellites, and if there's a bias in the frequency, that shows up as part of the errors in the estimates. There are differences between sensors, and they tend to be noticeable in IMERG. As I said, the different sensors see different aspects of the same scene based on their characteristics of the individual sensors. And so we try to fix these problems. If you've ever combined data sets, you know what I'm talking about. But there's just a limit to how well we can do that. The vastly preferable thing is that we get good inputs in the first place. We're best in the tropical ocean, and then as we go toward colder conditions and complex terrain, we have more problems. So this is what the GPCP climatology looks like. It looks a lot like the climatology from IMERG, although there are some differences, particularly this band in the Southern Ocean. I sort of refer to the Southern Ocean as the last great unknown in precipitation. There's not many observations down there for a really good reason. In the first place, there's essentially no land. In the second place, if you've ever talked to people who have done cruises down there, it's not necessarily a nice place to be. So the general layout, if you know your basic meteorology, you see the ITCZ, you see the South Pacific convergence zone, the mid-latitude storm tracks, northern and southern hemisphere, and then dry subtropical highs. Over land, they're deserts. Over the ocean, it's ocean desert. And then there's very light precipitation at the poles, which we don't do a real good job at. So here's a comparison of GPCP and IMERG final. This was done before we got, or no, this is actually, whoops, pay no attention to the blue labeling. This actually does the newer one that goes back to 1998. What you see is that in general, very different algorithms from IMERG and GPCP give you a pretty consistent picture. There is an offset. GPCP version 3.3 is somewhat higher. We sort of believe this to be correct, but there's still a topic of discussion. When you start looking in more detail, you do see some differences. They're further apart here back in the early 2000s, moved together around 2010, and so on. This heavy black line is where we switched from sorry, it's not. This black line should be 1 year over. Oh dear. When I changed the background diagram, I didn't change the line. Okay. The black line tells you that there's a switch from trim to GPM, but it should be a year to the right. One of the other things that I want to demonstrate is that land and ocean, so the bottom line is land. They're essentially the same because the gauges dominate. Land and ocean tend to move in opposite directions during ENSO events. And so in this La Nina, we have the ocean going down, land going up. In this El Nino, it's the reverse. So the old classic textbooks about ENSO, El Ninos, is like, oh, precipitation goes down. Well, no, it's compensated over the ocean. And so the total global precipitation has a very small change as you go between plus and minus ENSO events. In general, we would say the GPCP is preferred for climate analysis because it's more homogeneous. It sort of depends on what you want to do. Sticking with climatology, I will point out this is not what we do. This is from GIS and the AMIP in the lower left, CMIP in the lower right. These are the temperature trends over 1979 to various times. The longest period here in the upper right, a consistent time period with the AMIP and CMIP is in the upper left. What you see is that pretty much every place, the temperature trend is positive. I show you this because this is the corresponding trend in precipitation. GPCP in the upper left to 2014, consistent time period with the model stuff, and the longer in the upper right, just to demonstrate that adding a few more years doesn't change it that much. What you see is that the AMIP does a reasonable job of reproducing a number of the major features, and the CMIP, for what it's worth, this is CMIP 6, doesn't get the amplitude. And it's even worse because it's a little bit smeary, but if you could read the color bar numbers down here, it's actually multiplied by like a factor of 3, I think, to get any kind of variation in color at all. It's just really too flat. The reason to show this, one reason to show this is to say, because the global trend is actually very small, but the regional trends are large. And if you know your math, what this should alert you to is that if you have large opposing numbers, if you're going to have trust in the total of those large opposing numbers, you need to know each of those large numbers to the accuracy of what's left, what the residual is when you add them together. And so, the basic thing here is that we're right on the ragged edge of being able to say that there is a small global increase in precipitation, but so we think we have the sign right, but getting the value is really tough. On the other hand, regionally, the changes are pretty big and probably not that bad. Okay. Looking a little more in detail, since I'm talking to an ocean group, I thought I should try to come up with some ocean validation. It's very sparse, but recently one of my colleagues, Daniel Waters, who's now at University of Oklahoma, has gone through the so-called GPM validation network. It is that the validation network is only set up to take radar scans when there is a GPM core observatory overpass. So this is limited to a validation of the IMERG GMI, but it's at least representative of what we think is going on for IMERG as a whole. This is from the pre-boost era of GPM, when it was pretty homogeneous, validation network version 2.4. So these are ground radars, and the map shows you where they are located. There are 2 in Alaska, 21 around the edge of Conus. There's a few in Brazil, and there's a scattering of tropical as well. Okay, so when you look at this, the paper from which this is drawn was intended to show how version 6, the old IMERG, and the new version 7 now, well, new at the time, version 7, compare. And what you see is that in version 6, if you happen to have used IMERG or looked at it, version 6 of the high latitudes turned out to have a fairly substantial positive bias, which we didn't understand at the time that we created it. We thought we were doing a good job, but that's why you have new versions. In the new version, we fixed that. And so when you look at the ocean data from those 2 coastal radars in Alaska, it's Middleton Island and Nome. We kill it. We fix the problem. For other regions, the biases are not as large, and the change between 6 and 7 was not that remarkable, because what we were doing in the high latitudes, we were not doing in the low latitudes. So we're still sort of ending up. And so note this, if you remember, GPCP version 3 was high compared to IMERG. And what you see is, sure enough, over the ocean regions, GPCP would probably prove out higher, closer to a neutral bias. I haven't done this in detail, but sort of how it would look. In terms of correlation, which tells you about sort of the scene-to-scene variations, remember, bias is what's left after you do a lot of averaging. Correlation is a way of telling you about the random error. Version 7 was a notable improvement from version 6. It is the case, if you look across, there are multiple bars here because it's the various stages of going from just the input data to the final or the complete IMERG product. What you tend to see is that there's a slight degradation in the correlation. That basically says that we're optimizing things other than correlation as we go through these various steps, in order to get a product which, in some aggregate sense, we think is more accurate. So it's, so you lose some correlation, but it's not terrible. Looking specifically in the high latitude oceans, this gives you some sense of what happens with normalized error as a function of the precipitation rate. And this is fairly typical, that you tend to be, normalized error tends to be low at the high rates and then go high at the low rates. It's partly built in the fact that you can't have negative precipitation. So when you get to these low rates, the wrong positive values can't be offset by wrong negative values. You only have the positive values. But there's also an issue at the low end, the indeterminacy of, the satellites lose skill. And so you end up with a higher fractional error. Okay, here's monthly atoll sites. So these are depicted here in the lower left. This is the Pac-Ring Pacific Atoll location specifically. We filter out, we don't use the high and even the low islands. These are only the atolls. Basically, it's a chunk of coral sticking up high enough that you can put a rain gauge on. People live there and will take the observations. And so we think of these as representative of what's happening over the ocean. You will see, so as a function of these are monthly rain rates. We don't have a large collection of, even this is not, it's not that many. We don't have a large enough collection of daily rain rates to do this usefully. But what you see is that IMERG is pretty unbiased, at least in the monthly. And then GPCP, this is a version 3, is fairly unbiased at the low end and sort of trails off more, I would say, than IMERG at the high end. The table gives you some sense of what the biases are. Sure enough, the GPCP is lower. Remember, we're now on version 3.3, which is higher overall. So we would have maybe even a positive bias. We haven't done that plot yet. It's too, we just got out the version 3.3 data. By comparison, here's MERA2 and ERA5, looking pretty good in terms of bias at the monthly scale, where the models have trouble, and I don't think this is news to most of this audience. The models have trouble at the sort of the hourly scale because they don't do a good job with convection. And so at high latitudes, the models, if you did the same plot in Alaska, the models would look really good. But at the low latitudes where it's driven by convection, they don't do as well. Okay, so rocketing to the end here, I've got a few final comments. Just to remind you that the CDR, which is GPCP, and the HRPP, of which IMERG is an example, have somewhat different goals. And I would claim that they're arguably state-of-the-art examples. IMERG in particular, GSMAP and CMORPH at least should be considered. GPCP right now, I would be hard-pressed to name another strong competitor from the observation side. Obviously, on the model side, you've got things like MERA and ERA5. I showed, well, at least waved my hands at, the average global precipitation has a positive trend, but it's really the regional changes that are important. Unlike temperature, the regional changes are large and both positive and negative. Finally, in terms of those patterns, the models tend to get the global time series right. Regional patterns, not bad, say, but with either less or much less variation depending on which kind of model it is. Here's my email address. I really do answer questions, and it's like if I was running a company, I would demonstrate the success of my product with a profit sheet. But in the government, you demonstrate the success of your product by having users who actually can use the data successfully. So to that end, I talk to people a lot. So please ask questions. With that, I'm done. There's a bunch more slides. If you get the slides, there's lots of bonus slides that will have other things that you might want to ask about offline. With that, I'll stop and entertain questions.
Thank you, George. Questions? And maybe I can start by just asking a quick clarifying question. You showed the difference between the polar orbiters and the geostationary satellites What's the rough latitude of transition, and does that lead to a sort of visible discontinuity in the products, or?
Yeah, that's a good question. If I go back to this, so here's the long-term climatology,
Mhm.
and you really, maybe by design, we work really hard so that the edge of the IR is not obvious. So the polar arbiters are the ones that take you all the way to the pole. So somewhere around 60 degrees north is around the top of the Gulf of Alaska. So yeah, you might say, yeah, maybe there's a little bit something going on here, but over most of the range, you really don't see. It's a little bit harder in the Southern Ocean because we know less about what things should look like. This is the best estimate right now from IMERG. If you go, let's see if I can just zoom to it. Yeah, this is the corresponding thing in GPCP. Once again, if you're going to see a break, it ought to be somewhere a little bit south of 60 degrees north, a little bit north of 60 degrees south. We've done a pretty good job of sort of papering over that change, but you will see that there's a distinct difference between what GPCP shows in the Southern Ocean and what IMERG shows. But that's in the zone of where the IR, this drop off at the edge of the storm track in GPCP is within the range of the IR. So this is not a data set change. This is actually in how we the data.
Thanks. Lisanne Yu has her hand up.
Hi, George. Thank you for the great talk and really insightful. I appreciate you leading the group in producing the two very useful data sets. And for us, for ocean, and we pair, I'm doing the evaporation product, so often pair with GPCP or IMERG for ocean water cycle and a salinity study. I know I appreciate your comments that GPCP is for long-term perspective and IMERG for short-term variability. So another question is like for global ocean budget, freshwater budget, E months, P months are, which one is better to use? Because I found the GPCP and IMERG have different budget over the ocean, global ocean, and yes, that's the picture you show, and over the lane is pretty much converge, but also ocean, you have like sometimes you have a 5 to 8% difference between the two products.
Yeah, and so in the past, GPCP version 2.3, which is what we put out for a long time and is actually still available through NOAA, was considered low by 5 to 8%. When we went to version 3.2, so there were some intermediate 3.1, 3.0, but the first really big advance was version 3.2. That went up non-trivially, and it was fairly, I'm working from memory here, but it was fairly consistent with version 6 IMERG. Now we're up to version 7 IMERG, which is relatively consistent with version 6, and 3.3, which 3.3 is the highest, I think, of all of those. So we're back to this question, and I can't give you an answer yet because 3.3 just came out the middle of last month. So
Right.
we haven't really had a chance to do the analysis. One of the things that we queued on in knowing that version 2.3 was low is that there was a NASA news project which did a 10-year aggregate, water budget for the globe. And so as part of that, they tried to estimate who was low and who was high of the various inputs to the water budget. And it seemed that GPCP was low by like 5 to 8%. So I'm now in a position of sort of looking at you and saying, if you if you have all the other parts of the products, or the other products part of the water budget, what's left? You know, is GPCP high? Is IMERG low? I'm not sure.
I just like feel GPCP I haven't tried the 3.3. I was like in the process working with Ali and other members of relation, and they told me GPCP 3.3 just out last month, so I have got a chance to look at the GPCP. But from my experience working with 6B, I merged 6B and GPCP 3.2. I think GPCP 3 IMERG is slightly higher than GPCP, and which is better balance with our new evaporation product. So right now the contradiction is like we try to close to a series EBAF data set, but meanwhile, if we close too much to the series, and then we deviate further from IMERG. So it seems like IMERG and the series are slightly off balance. So from the energy balance perspective, I would like to see GPCP or IMERG slightly increased.
Yeah. So I would really appreciate working with you and whoever else that you're working with offline, and we need to know this, because you know you live by the calibration, you die by the calibration. So there's some, you know, a number of calibrations that have been put in here, and it's different in 3.3 than it was in 3.2 in GPCP. And so, you know, that's what drives the higher values, is a change in the calibrator. And so I didn't say this, but I should have. It is that in addition to the routine month-to-month calibration by the microwave of the infrared, there's a background seasonal calibration, which is based on Ali Barangi's MCTG climatology of, yeah, it includes CloudSat and TG, GPM. Yeah, it's not, it wouldn't be the biggest surprise in the world if it turned out that the calibrator maybe wasn't quite on that background calibration. So I would really like to, you know, make contact with your group and just sort of see how you're doing as you step into this, because we don't have the background in all the other data sets to know how to do this ourselves.
Sure, I will send you email later on, but I'm working with Ali Beringer right now, collaborate with him.
Yeah.
Okay. Thank you very much.
Thanks. Other questions? Melanie Fewings has her hand up.
Oh, hi, George. Thanks very much for this nice talk. I was curious, what's your vision for what the ideal observing system for rain globally would be?
Oh, well, that's a really great decadal survey question. So what we've got going right now is pretty good, which is to say we have a calibrating satellite, which is currently the core observatory for GPM, which has a radar and a radiometer. So we can use those to do calibrations first at the radiometric level of the individual satellites, and then at the precipitation level. So we do two calibrations. Before we even get to the point of computing precipitation, all of the input radiometers have been intercalibrated to the GMI. And then once we get past that, then we do an intercalibration at the precipitation level to the combined radar radiometer, which should be the best estimate. But the problem is, one relatively narrow swath radar in space isn't going to give you the answer. It can only do calibration. So we want to continue that in the future. As you know, someday GPM is going to end. And so the question is, what's the next calibrator? After that, then the question is, can we maintain a constellation, a virtual constellation of sensors with wide selections of channels and good quality? Currently, the small sats are the thing. People are all excited. They're smaller, faster, cheaper. And so that's fine with me as long as they give us the quality of data and the selection of channels that we need. So I'm sort of pushing back on the industry a little bit to give us what we actually need scientifically, not just in terms of the budget and the form factor of the satellite. Would it be nice to have more frequent observations than 90% of the time within 3 hours? Yes, because not so much for the ocean perhaps, but certainly over land. Flash flooding requires observations at frequently less than a 2-hour interval. And so in remote areas or underdeveloped countries that don't have radars, if we're giving them data every 3 to 6 hours, it's not optimal for that kind of high value application. So we would like to keep we've got a mix right now of the sounders and the imagers, total of about 11 or 12 such satellites with really, science quality data. We really need to continue that. If we could get some radars in space, you have perhaps heard various commercial companies talking about putting up radars. That would be great. Radar is really great. But if not, we're capable with the radiometers as long as the data quality and density doesn't go down too much.
Are you actually, I haven't, well, sorry.
And one other thing to say, even though I'm a satellite guy by job title, I'm a meteorologist. I'm shameless. I will take data from any place. And in particular, in this case, we desperately need the gauges. It would be nice to have the surface radars, but that's a harder sell. But, surface gauges are just critical to providing the tie points to the satellite estimates, which give you pretty decent relative estimates, but struggle sometimes with doing the absolute values. So we really need gauges, and the global gauge assembly is in a continuing state of collapse. We have to keep going back to the data providers and say, no, we really need the gauges. Please send the gauges. Okay, now I'm done.
Thanks. Other questions? George, with regard to gauges, you said you don't use island stations, although you use the atolls. Do you use buoy data at all, or data from ships?
Yes. We are somewhat, the funding we've got doesn't let us do as much of this as I would like to. But yes, the buoys are really an underutilized resource. To be blunt, the atolls are an underutilized resource. We don't really point to these as much as we should. And I think, in the next round, this is, if I have ocean people pounding me on what the quality is over the ocean, it will help me justify spending time looking at ocean data more. The island stations, this, like Hawaii has a number of gauges, but it's also complex terrain. And this is a typical problem. The islands that are not atolls tend to have complex terrain. And so they start forcing precipitation, which is hard for the satellite sensors to accurately retrieve. But yeah, the buoy network is, I have twiddled with at various times, and to be fair, I need to get back to that.
I have a follow-up question. Sorry, I don't have a hand raised feature. This is Elizabeth Thompson. Hi, George.
Hi.
Thanks for a great talk. As you know, we've worked a little bit with your team to provide an ocean validation data set from the passive aquatic listeners that are like a super gauge where they're representative of like a 5-kilometer area, which is advantageous for a lot of reasons.
Which is great. Yeah.
I feel like that's such a great instrument, especially at the low rain rates that models struggle with. And to me, like I wish they were out there. I wish they were on the buoys. But my understanding is like the current technology is that they have to be deployed and then recovered. And they don't have this like real-time capability that probably your team needs. I was wondering like, and I'm not an acoustician or an engineer. I think I haven't talked to anybody doing this, like whether the technology could be pushed to more real-time or less regionally sensitive. If that were more capable to like a real-time aspect rather than a research instrument that you get the data 2 years later upon recovery, like would that make a difference for you all, or and have you guys used that validation data set retrospectively?
That's a really good question. So the problem that you face. So the problem you face with integrating these data as input is number one, latency, which you've mentioned. But the other is that if they're sufficiently sparse, it's sort of like, wow.
That's still an issue for you guys, and that's the main issue behind using the buoys, right? That and vandalism, like
exactly. Yeah, and so I mean, goodness knows over land, if we have one gauge in Angola, we use it. But to be fair, those data don't come to us; they go to the GPCC. We are also working with Chris Funk, who's at Climate Hazard Center in UC Santa Barbara. And if those folks could get these data on a timely basis, that's really where they would get integrated most likely. That we would treat these as gauges. Yeah, this might be something to pursue offline. Because on the one hand, yeah, they're really sparse, but on the other hand, having something might be better than nothing.
Especially with their spatial, like they're better spatial coverage than a spot gauge. Yeah.
I certainly appreciate, that in 1998, I sat in Kwajalein Harbor on the Ron Brown talking to the guy that started PALS.
Jeff Nyston. Yeah.
Jeff Nyston.
Yeah.
And that was a long time ago now, and we've just never gotten to the point of this getting critical mass. So if you have a concept, let's talk.
Yeah, I feel like we need to assemble a team to like push the technology a little further, but the science is there. But yeah, we can think about it more. And
yeah, in particular, the notion of them of actually sensing the cone, the area, not just a point, is really great.
Yeah, well, thanks for your effort on this. Thanks.
Thanks. Other questions? Megan Cronin has her hand up.
Yeah, hi. Hi, George. Nice talk. The tau array is being recapitalized right now. And in the new design, every single mooring is going to have a rain gauge in the tropical Pacific. And so we will go from having 4 rain gauges, 2 of which are in the subsidence region of no rainfall, to having rainfall at something like 50 sites, including in the ITCZ region. And I think that the community as a whole needs to show a lot of love towards these rain gauges to ensure their quality. We need to use that data. We need to kind of hover over it and make sure that they are, the highest kinds of data that we want, because it is really truly remarkable what is going to be done with this recapitalization of the tropical Pacific buoy array.
Yeah, I have to say, I had heard about the recapitalization. I didn't realize it was that many.
Yeah.
Admittedly, still sparsely sampled, but so I think actually, as I was saying it, this is the first time I've conceptualized that maybe the right place for these data to go is the gauge centers, GPCC, CHC, what's the one in England? It'll come to me later. Anyway, the gauge centers, because our use of these is really tied to the analysis that they do. Because they're so sparse over the ocean, I think I'd have to think about this, but basically, if it's in the ocean, we know that that site is a buoy. We'll use it in its region. We won't expect.
Yeah, what the buoys really give is the high resolution. I mean, we can get the 1 minute rain rates, and so perhaps that's something to capitalize on rather than the spatial information.
Well, so I would go both ways. The spatial, if we have even a few sparse places around the ocean, it's at least worth thinking about whether the gauge centers can make use of these in their analyses. GPCC already does stations over island, uses the island stations. We throw it away because of the orographic problems for us, but they include them. So they might be open to including the buoys. But then, yeah, once again, I think offline, we probably need to have a discussion with both the PALs and the TAOs to make sure that we honor the the investment that's being made and should benefit us.
Yeah, this recapitalization is happening right now. So the 95 West and 110 West lines, I think, might be already done or in the process. And then the Western Pacific and Central Pacific are getting rolled out in August and September. So
Wow.
Watch out for that. Okay, great.
And is this, in the old scheme was it was download after retrieval?
No, it's in real time.
It's in real time. So it's transmitted. I think, but I mean, the old days, I feel like they had to retrieve the buoys and download the data.
Or there was some QC that was done post-processing. And this is what we need to kind of watch out for. And I'm not really prepared to say what their kind of process is, but let's pay attention.
Okay. Yeah. And so like I said, let's get together. I've said this to several people, and